capacitor question, we have four plates given in this question, and initially the plates are charged and after that the plates are grounded. Two plates are grounded. This is, let's say, A plate, B plate, C plate and D plate. A and C are grounded. Now in this case, first thing we should remember is that to get the total potential at any point in this system equal to 0, means potential at any plate, if we want to get 0, then for that we have to take the total charge on the system is equal to 0, because if there is any charge on any of the plates, means if there is some net charge in the system, there would be some electric field in the system. And if you go from infinity to this system, there would be some electric field and there would be some potential at each of these capacitors, but we know that potential is 0 and these two, so the total charge should be 0 so that the electric field becomes 0. In this case of parallel plates capacitor, the electric field is taken independent of the distance. Electric field is constant, and because it does not depend on the distance, it depends only on the charge. To get the 0 electric field everywhere, we have to make sure the charge is also 0 in this system. So that's why the total charge on the system is 0, and the total charge on the system divided by 2 is the charge on the extreme plates outer sides. So that's why we get 0 and 0 at these two sides. Now after this, we also know that some charge may flow from this plate, some charge may flow from this plate, and they can be, and these plates are actually some thickness of some thickness, and they can be treated like capacitors. So we can draw them like this: plate A, plate B, plate C, and the plate D. This side has 0 charge, this side has 0 charge. This P has total charge 2Q and this is total charge 4Q, while it had initially Q charge and this had initially 3Q charge, but some charge flowed out of it, after we grounded it. We grounded these two together, so these two are grounded simultaneously, and in that case we get, these are the potentials: 0 at this side, 0 at this side. On if the potential is 0 at this side, we get 4Q at this side and minus 4Q should be at this side. Also we know that this body is at some potential VB and this is at some VA potential and this is at VC potential. These two potentials are same, so the potential difference between these two, VB minus VA, let's say it is equal to delta V, and that would also be equal to VB minus VC, because VA and VC are same. And this can be treated like a capacitor. For example, this plate can be drawn like this. This is the A plate. The B plate can be drawn like this, C plate like this, and the D plate. This is capacitor and another capacitor and the third capacitor. Here we grounded this and this C point. This side has 0 charge, this side has 0 charge, and this side has 4Q, this side has minus 4Q. In this case, some charge flown out of it, and the total charge on this part is, let's say, Q1, and this is, let's say, minus, let's say this is Q1 positive, so we'll get a minus Q1 here, and on this side we will get some Q charge, let's say Q2 charge, and minus Q2 charge, and the sum, and we know that total charge on the system is equal to 0. It means, okay, all charges are satisfied. And also we know that this plate B has total charge of 2Q, and that should be equal to this minus Q1. Let's say this is plus Q2 and this is minus Q2, so in this case we will get minus Q1 plus Q2, that is equal to this 2Q charge. I don't know the sign of this q1 and q2. I'm just assuming it. So in this case we get this 2q should be 2q. We can assume that 2q plus q1 should be equal to q2 according to this sign. q2 is positive here and q1 is negative here. Now in this case we also know that these two are capacitors and potential difference across these two are same. So total charge on them divided by the capacitance is equal to the potential difference. It implies the q2 charge on it divided by, oh, this is at higher potential side and this is the lower potential side. The electric field points from the higher to the lower potential. So let's say this is also plus q and this is minus q. So we get both as positive. So it means that q2 is equal to 2q minus q1, and the q2 divided by this c, both are identical capacitors, so capacitance is same for them, and that q2 by c is equal to the 2q, sorry, q1 by c, and this q1 by c can be written as, sorry, q2 by c can be written as 2q minus q1, and that is equal to q divided by c. So c gets cancelled and we get 2q is equal to 2q1, that gives q is equal to, sorry, this is 2q, so okay, 2q is equal to q1. So we get total charge is equal to q1. So it means at this side we will get q and at this side also we will get q charge. Similarly here we get minus q and here we get minus q. So we can say that initially the charge was 3q here, but now it becomes 3q. So the total charge flown out of it should be 0. Sorry, it is minus 5q. It is minus 4q. So total charge is minus. So we need 8q charge to be flown out of it. And here at this side, the charge is 2q. And on this side, which had initially q charge, now it is having minus q charge. So it gets total 2q charge flown out of it. So that's how we can analyze it. First of all, if any one of them is grounded, the total charge on the system would be equal to 0, and these outer sides will have 0 charge. And after that we can write the charge distributions as much as possible, and then we can use this this charge conservation for this plate. And we know that the q1 and q2 would be same for both of them, and this helps us in relating the charge q with q. That's it. And also, if one more case, let's say we have 3 plates and it is given some q charge plus q charge, and initially in the system that charge q will be distributed symmetrically, q by 2 here and q by 2 here, and minus q by 2 will settle here, minus q by 2 settles here, q by 2 here and q by 2 here. So we can say that the total charge on the system is q, and half of it will be the charge here and on this sides. And this way we can write the configuration also, charge distributions also. And now if this, sorry, this is a switch here, let's say, and there is also a switch here, and these are grounded. Now if only this switch is closed and this is open, means this switch is closed first, then in that case there would be some zero potential at this, and to get the zero potential here we need total charge on this system to be equal to 0, because q charge is here, 0 charge is total here. We need a minus q charge on this plate, so it means we get a minus q charge on this plate, q charge on this plate, and because there is minus q charge on this plate and total charge on this plate is q, which is constant, so we get total q charge settling at this side, and minus q charge settling at this side, and this side will get zero charge, and this other side, because this is having a zero charge also, so this will be having zero charge at both sides when it is grounded and it is open. Now if I, so let's say this is switch and this is ground. Now if I close this switch after this is closed, in this case nothing would happen, because the potential at this point is zero already. So even if I ground it, the potential will remain zero, nothing would happen in this case, no charge distribution occurs. But if I close these two switches simultaneously, then in that case I cannot tell what is the distribution, but probably it is symmetrical, we can say that. And let's say this side gets some q2 charge and this side gets some q1 charge, so this will get minus q1, this gets plus q1, this gets some q2 charge minus, and because we know that the total charge on the system should be zero because these are grounded, so it means we should get q2 q1, sorry, q2 plus and minus q2, q1 plus and minus q1, and the charge on this side should be equal to 0, because we know that total charge on the system is 0, so this side will have 0 charge in this case. So the system will look like this: some q1 charge here, minus, plus q1 charge here, plus q2 and minus q1, and 0 charge at this side. So now in this case the total charge on the system is 0, but the q1 plus q2 is equal to q, and also we know that the potential difference between these two is same, so we get q2 is equal to, so q2 by c is equal to q1 by c in both cases, so we get q1 is equal to q2, and this means this is q by 2, this is q by 2, this is minus q by 2, and this is minus q by 2. So we get a different systems when this was the case when both are simultaneously grounded, and this is the case when one was grounded before, one was grounded earlier than the other. Now let's move to the current chapter. We have some kind of circuits, we have few methods like mirror image or symmetry we use. So the symmetry says that if we have a circuit here like this one, a very simple circuit, this is, let's say, point B and this is A, and the current is flowing through this circuit, and these are, let's say, equal resistances R and R. Now in this case we know that the amount, due to the symmetry, we know that the current flowing through this, let's say it is I1 and it is I2 through this, and the current coming out of it, let's say it is I3 and it is I4, and there would be some current flowing through it I5, let's say. Now in this case, from the symmetry we can say that if we flip the voltage supply, then in that case the current will go from this side to this side, and because the system is symmetrical, this I3 will be just copying this value I1, and because of the symmetry, the amount of current, because from these two sides, let's say it is at V by 2 potential and it is at minus V by 2 potential, due to the symmetry, the, we can say that the current going out of it should be same as the current coming into it. So I1 becomes equal to I3 because of this symmetry, and this I2 becomes equal to I4, and because the current I2 is equal to I4, the current is flowing directly in this path, so there is no use of this current, means this resistor is of no use, because no current is flowing through it. All the current is passing straight in these resistors and no current will pass through it. So we can just remove this resistor and the circuit breaks down to this simple form. So that is the use of symmetry. We have to think of the current. In case of symmetry, we see which resistors are having the same currents, and in that case, if the current is flowing just same amount as here, the current would be, if the current going in is same as the current going out from here, the current will not go in this resistor, so that resistor can be removed from the circuit. That is the first point. And now the second thing is, if we have a circuit like this, let's say a resistor is here and I have a resistor connected to it like this. In this sense, now let's say it is resistance R, it is resistance R, and this is point A and this is point B. In this case, the total current flowing through this is, let's say, I1, I2 and I3. Now in this case, because of the symmetry, we can say that these are symmetrical about this axis. This R is symmetric, means symmetrically these two are identical, so the current flowing in this would be identical also, means I1 should be equal to I3. It means we can say that I1 current flows from this, I1 current flows from this, and some I minus I1 current flows from this resistor. And because these two are having the same current through it and these two are parallel, we can say that the these two resistors can be replaced by a single resistance, let's say R dash, so that the current flowing through them becomes 2 times of I1, and this is normal I2 current flowing through this. So to get the 2 times of I1 current across the same potential difference, we need to get the half of the resistance that comes from the parallel addition. So we can simply say that if two resistors are like this symmetrically about this line, we can just add them parallelly and accept this middle one because there is nothing parallel to it, symmetrical to it. So these two resistors can be added parallelly and give a net resistance which is R by 2, which will give us 2 times of I current through it. This is generally useful in the case of a very complicated figure in which one side is symmetrical to the other side, means these two are identical side on the both sides. Then we can just flip it on the other side and take the, and also in that case, let's take a bigger figure. Some resistor R1 here, this is R1, this is R2, this is R3, this is R4, and then we have this is R5, and similarly we have a resistor set here, and these two resistance are equal. Let's say this is R2, this is R3, this is R5, and this is R4. Now in this case, because of the symmetry, the current is flowing this direction. So because of the symmetry, we can say that the current through this would be equal to the current through this. The current through this is equal to the current through this, and same all over. Because they are having the same currents, we can say that the these two can be taken parallelly, means these two wires can be brought parallel to each other. You can flip it, and when these two resistors get parallel to each other, they become so close, and the total resistance of the circuits, let's say it is R naught, and this would this whole resistance can be treated like R naught by 2. If I add this to it, means if I remove this part and replace this resistor with this another resistor, that would be equal to R naught by 2, because I current is flowing in this and I1 current is flowing in this also. So the total current gets double if I add them parallelly, and that means the total resistance would be half because the potential difference is same. So it means that we can just flip it on the other side, and the total resistance of this whole part, just because we are adding them parallelly, the total resistance would become half of the initial. And also this can be treated like adding this to this, adding this resistor to this resistor, and similarly this resistor to this corresponding resistors. But overall this symmetry is simply saying that the total resistance of this part becomes half if we get a symmetrical resistor here. Also, if I add one more set of resistors like this and I join it at these 2 points, then the total resistance will become R naught by 3, because means of this part, if I add all these 3 parts, means except this, if I add this similar resistance set to this, so I will get 3 sets, and if I add them all parallelly, I will get total R naught by 3 resistance, and the total circuit will look like this: R naught by 3 plus this R1 resistors, and that gets simplified into this form. Now the superposition principle in the grid circuit. In the grid circuit, we have, let's say we have an infinite grid, and in that case we have, let's say each of the joints have this length of resistance R, means this wire is of resistance R between each joints, and this is, let's say, point B and this is A point. We have to find out the equivalent resistance between this AB. So to get this, we have to let the system, this is the infinite grid system, and we take this point A alone and we provide some V by 2 potential to it, and in that case there would be some, at the infinite distance the potential can be taken to be 0, and at this point the potential is V by 2, so the current will flow from this. Let's say the current flowing is I, and sorry, total current flowing through this is, let's say, I, so it will become I by 4, I by 4, I by 4. Due to the symmetry, the current in all of this direction would be I by 4. Similarly, if I take the B circuit, and this point B is, let's say, having some minus V by 2 potential, so the total current coming out of it is symmetrically I, and I by 2 current is going into it, I by 2, I by 2 from all these 4 sides. I by 2 current goes in, sorry, I by 4 current goes in, and it becomes equal to I. Now in this case, the total current in the circuit is going I inward, and in this case the current coming outward is I. Now if I join these two circuits together, if I superimpose them, let's say this is the A and this is the B, this was provided V by 2 potential, it was provided minus V by 2 potential, some I current was going inside, some I current was going out of it, and it was having some I by 2, I by 4 current in this direction, and this A was also providing some I by 4 current in this direction. So total current here would be I by 2 between this AB. So we can say that the total potential difference is V, and we know that the total resistance here is, by applying the Kirchhoff circuital law, we can say that V is equal to the current into the resistance between them, which is R. This resistance is R, so R is equal to I by 2 into R, and V by I is equal to R by 2. That should be equal to the equivalent resistance.